Hello, good morning, and welcome everyone to CS300 Introduction to Algorithms. And today we're going to continue our discussion of graph algorithms for higher type graph problems, basically for minimal spanning tree. That's our goal. And I'm going to share with you the slides so that we can resume the discussion. So here you see the specification as a reminder for minimum spanning tree, and the picture that illustrates the problem. We're given a complete graph with edge weights. So whenever in this graph there's no edge, then we can without assume that the edge is present but has weight infinity. So to make sure that it will not be present in any reasonable minimal spanning tree, because that will never be a minimal spanning tree. And the goal is to find a subset of the edges that is, first condition, a tree. So it must be connected and must be spanning. That means it must make sure that any vertex can be reached from any other vertex using all the edges from that subset instead of the entire set. And the third condition is that it must be minimum, must be of minimal weight. And this minimal weight condition already makes sure that the resulting subset of edges is a tree. Remember, what is a tree? A tree is a connected graph without cycles. And but the condition of having no cycle is kind of redundant in this setting, because if minimum spanning graph has a cycle, then we can just drop the most expensive edge, for example, in that cycle, and still have spanning graph of less weight. So what we started with, therefore, cannot have been the least weight spanning graph contradiction. So to summarize, we can say we're looking for minimum spanning trees, or we can say we're looking for minimum spanning graphs. That's the same. And to make things well defined, we're not actually asking for the minimum spanning graph, because that need not be unique. Instead, we're looking for the weight of a minimum spanning graph, because that is unique. And from that weight, actually our algorithms will, as a side product, produce a minimum spanning tree, a minimum spanning graph out of several possibles. So that's a specification of the problem. And let's look at some first algorithms, because the naive algorithm, just trying all possible spanning graphs or all possible graphs, involves exponentially many graphs, and therefore is an exponential time algorithm, which is not what we really want here, right? So the first algorithm we're discussing, and that's actually what some of your homework assignment to implement, is Prim's algorithm, right? So you have this homework assignment that asks to implement Prim's algorithm. So here's Prim's algorithm on a very rough meta level. We avoid at this point to overly formalize it in terms of pseudocode even, not to mention actual code, because the algorithm is an abstract concept that can be described in various ways, and we make an effort, a point of distinguishing between an algorithm and a program. So here you see an algorithm, description of the algorithm. The idea is to initialize a tree with a single vertex, and then to gradually grow a tree from that vertex a tree with a property that it spans larger and larger parts of the initial graph. So at the end, it will be guaranteed to span the entire graph, and the growing process is governed in such a way to make sure that the result is actually a minimum spanning tree. And to this end, the algorithm, Prim's algorithm, in each round chooses to add the vertex to add to the partial spanning tree is a vertex to have least distance to the tentative, to the previous spanning tree. So we can consider this as growing a partial spanning tree, which spans only part of the original graph, and from the graph that is not covered yet, is not being spanned yet, the algorithm has a choice which vertex to add to the partial tree. And that's kind of the key idea of Prim, to choose the vertex which is closest to the closest to the partial tree. Okay, so here, yes, finally the description: initialize a tree with a single vertex, and then grow a partial tree by one edge in this phase, in this round, and the edge is to be chosen so that it has least weight among all edges that connect the partial tree to the rest of the graph that is not yet covered by the partial tree. And then, this requires choosing a minimum weight edge from a subset of the edges, namely from the edges on the boundary of the current partial tree. And this means that underlying Prim's algorithm is actually a priority queue. And there are various ways of implementing, of realizing a priority queue with various actual costs. And depending on how we implement the priority queue, that affects the cost of Prim's algorithm. So, and yes, in your homework assignment, I understand that the TAs chose to let you give you freedom which implementation of a priority queue to choose. Okay, so in this phase, one edge has been selected and added, and thus the partial tree has been grown, and then repeat until all vertices in the graph are in the tree and therefore are covered by therefore the tree has become a spanning tree. Let's illustrate that with this example. So here's the graph. Here are weights, edge weights to the graph. And remember, our convention is that we only use positive edge weights. That's no loss of generality. We can avoid zero edge weights, and negative edge weights cause lots of problems. So we avoid that. And now we start with one vertex and grow from that vertex. So remember here, phase 2, choose an edge that connects the partial tree. Here the partial tree is a trivial tree to vertices that are not yet in the tree. All the remaining vertices are not yet in the tree, using the minimum weight edge. So from this partial tree, there are 3 edges outgoing from the tree, in this case from the vertex, and we choose the one with minimum weight, and this is the one with minimum weight 6. And add that. So far all other vertices have kind of distance infinity, and now we calculate, well, not the algorithm, but we, in our example, calculate the distance of the vertices outside of the tree to the tree, and choose the one vertex that is closest in weighted distance, or put differently, we choose the edge outgoing from the tree of least weight, and this is this edge. So this vertex is getting added to the tree according to Prim's algorithm. And then then the next round starts, and we need to update the weighted distances of the vertices that are not yet part of the tree to the tree. And so, for example, this vertex, which currently still has recorded to be of distance 9 to the tree, right? So every vertex in the tree has distance 0 to the tree, it's in the tree. This vertex is outside of the tree. It has a positive distance, it says it has distance 9. But now, actually, that we have added this vertex, the distance has decreased. This is a shorter or a lighter path to that vertex. So adding this, it decreases the distance. So we need to update this to 8. And similarly, this vertex that previously had distance infinity, it was not reachable in one step from the trivial tree of one vertex. Now it is reachable to the tree of 2 vertices using distance 10. So update operation. But let me keep emphasizing that all these distances are not really explicitly maintained by the data structure. Instead, they are maintained in the priority queue underlying the implementation of Prim's algorithm. Okay, so now continue next round. Choose a vertex which is closest. This is this vertex, right? 11, 10, 8. 8 is closest at this vertex. Thus, having grown the partial tree to consist of 3 nodes. And with this third new node, with this new node, we need to update again the neighbor vertices. So this vertex, which previously had distance 10, now boils down to have distance 1, right? This edge is much cheaper than this one. This vertex that used to have distance 11 now gets down to distance 3. And this vertex that used to have distance infinity now gets down to have distance 12. And here we are. Okay, so that's it. And now the next round, choose a vertex which is closest, but not in the tree. That's this one. And update the distances of the newly added, the neighbors of the newly added vertex. Yeah, that's an important thing. Only distances of vertices that are neighbors of the newly added vertex need to be updated. That will turn out to be beneficial in the algorithm, namely this one. Okay, add, next round, add a vertex, add this vertex, update the distances of its neighbors, update this distance from 12 to 5, update this distance from infinity to 4. And next round, choose the vertex which is closest, which is this one. Update the distance of its neighbors. Nothing is happening here, right? Then choose next round, choose the next vertex, update distances, nothing happens. Choose the next vertex. And now we have added all vertices. All vertices are now in the tree, and we are done. We have finished. The algorithm has terminated and has produced as fat edges here a tree, a spanning tree, and the claim is that it is a minimal spanning tree. So now we're already starting to analyze the correctness of the algorithm. And as I've argued, what the algorithm clearly produces is a tree, because that's kind of the loop invariant during each iteration here. Only one edge is added, and the edge is connecting the partial tree to a vertex which is not yet part of the tree, and therefore the edge being added is never causes a cycle, because a cycle would connect two vertices that are both part of the tree, but the edges that we add always connect a vertex in the tree to a vertex not in the tree. So yeah, to conclude the algorithm produces a tree, and it produces a spanning tree. Why does it produce a spanning tree? Because if in the end the algorithm terminates only after having added all vertices to the tree, and the tree by its very definition is connected and therefore spanning, and all vertices being part of the tree means the tree is spanning the original graph. So that's the second property. And the third property, the claim is that the algorithm produces a minimum weight spanning tree. Why does it produce a minimum weight spanning tree? That's again a consequence of, and this is a non-trivial part, a consequence of the loop invariant, namely that the algorithm always chooses the edge or edge of minimum weight from the edges that connect the tree to a vertex not yet in the tree. So this is kind of a yeah, later at the end of this course, we're going to talk about algorithmic paradigms, and one algorithmic paradigm is going to be greedy algorithm, and this is actually an example of a greedy algorithm, because the algorithm kind of greedily just in each round picks an edge of least weight connecting a vertex in the tree to a vertex not in the tree. So yeah, that's an example of a greedy algorithm. Other algorithmic paradigms are divide and conquer. We've discussed these, for example, when we talked about polynomial multiplication and so on. Anyway, so that concludes our exposition of Prim's algorithm that you can see here. And we need to discuss how to implement this higher level operations. As you recall, according to the virtues of computer science, we have to specify the primitive operations, right? That's one of the virtues. Which operations are we allowed to use when designing such algorithms? And the operations that we use here are certainly not primitive operations. Find the minimum weight edge is certainly not a primitive operations. Transfer the edge to the tree, that's we can translate that into a primitive operation using a suitable data structure for representing the subset of edges that form the tree. That's that's basically just going to be an array where we add one edge after the other, put it into the array, and thus increase the fill level of the array. We know how large the array will be, right? So in the end, the array will hold n edges, right? N minus 1 edges, sorry, because we're talking about a graph of n vertices, a graph of n vertices, and a tree over n vertices has n minus 1 edges always. And so we know we can prepare an array of size n minus 1 where we can store the numbers in each array entry. We can store the number of the next edge to be added to the tree. So that's a way of implementing this operation in a kind of primitive way. But the lesson to be learned here is describe an algorithm on this kind of higher level perspective is a great way of how to say, getting a bigger picture in algorithm design. So being tied to low level, to implementation issues causes what Knus called premature optimization is the root of all problems. So we avoid that, but still we need to figure out how to boil all the high level operations down to low level operations. And that's what we just achieved for this operation, transferred to the edge to the tree, but not about finding the minimum weight edge, because this is indeed going to be a high-level operation, an operation that is provided only by a priority queue, and how to implement a priority queue is an entirely different can of worms. So let's open this can of worms and look at the pseudocode. So less high-level perspective on Prim's algorithm. So what you see here is the initialization. So Q is an abbreviation for the priority queue used and maintained by the by Prim's algorithm, and while this priority queue of edges is non-empty, we extract no, I have priority queue of vertices. I'm sorry. We extract from the queue a vertex with least distance to the, so this du denotes the distance of the vertex u, which is not in the tree, to the tree. Let me say that again, that's an important point. So the priority queue right. So the priority queue stores the for each vertex in the queue its distance to the partial tree, which means the distance, least distance to any vertex in the partial tree. And the priority queue operation here is to extract a vertex which has least distance to any vertex in the partial tree, vertex which is outside of the partial tree, that's the members of the queue. So that's here we already have kind of a loop invariant, namely that at each stage, at each round, the priority queue contains precisely those vertices of the graph that are not part of the partial tree. And if this edge is has weight positive, then we add this edge to the tree, to the kind of array, which is stored in this data structure F that I mentioned before. And for each neighbor of this vertex U, we now need to update. Remember our demonstration animation, we need to update the distances of its neighbors. So previously this vertex U was not part of the partial tree, and now it has become part of the partial tree, and the neighbors of that vertex may have thus decreased in distance now that their neighbor U has become part of the partial tree. So we need to update them, and updating means checking what are the distances that we have recorded for these neighbors, distances to the partial tree, and compare this to the new distance, the distance of the newly added vertex to the newly added vertex. And if this new distance is less than the previously stored distance, then we should update that distance, and we should also make a record of that for the vertex whose distance has been updated, what is its neighbor in the tree. So, and here you see again the two operations, implicitly the two operations that constitute priority queue, namely extract min. Here we have the extract min operation. So this is an implicit call to the extract min operation, and a decrease key operation that we have here. So these two operations, and so these two operations together are the operations provided by a priority queue, and we need to discuss how the performance, how the computational cost of this algorithm depends on the cost of the single operations provided by a priority queue. So let's do that and record that the overall cost of Prim's algorithm is n times the cost of the extract min operation of the priority queue. Why is that? Because this loop here is executed precisely n times. This while loop is executed initially, all vertices are part in the priority queue, Ln vertices, and in each iteration of the loop, one vertex gets extracted, thus decreasing the size of this priority queue by 1. And that means after n iteration, the queue is empty. So it's really executed precisely n times. In the first iteration, any vertex gets extracted, and this is going to be kind of the start vertex, the root of the minimum spanning tree. Now let's discuss about the second operation, the decrease key operation. So superficially, we have here two nested loops, the outer loop being executed n times, and the inner loop being executed as many times as there are neighbors of the current vertex. And in the worst case, there can be as many as n neighbors, right? Any vertex can, n-1 to be precise, any vertex can have up to n-1 neighbors. But which is true, which is an accurate analysis, which means that in the worst case, there can be n squared calls to decrease key. But this is valid, but an overestimation if the graph is sparse, if the graph has a number of edges that is asymptotically less than n squared, then this operation here is called less than n squared time. More precisely, this operation is called in total a number of times m number of edges. So this is a tighter analysis, also correct, but tighter. And why is it tighter? Because observe that this inner loop, although it is part of a nested loop, the body of the inner loop is executed at most once for every edge. That's a crucial observation that we want to make here. So we have a current vertex U, and we have a neighbor V of the current vertex. And although the neighbor V might be considered several times, it could be a neighbor of the current vertex U, and it could reoccur later during another execution of the outer loop with a different vertex U prime, if V is also a neighbor of U prime. But in this case, there's an edge from U to V and an edge from U prime to V. And so actually any execution of the innermost loop body arises from an edge, and every edge is considered precisely once. The vertex V can be considered several times, but the edge that we're now looking at here, the edge from U to V, is considered at most once in every execution of the innermost loop body, and therefore the innermost loop body is executed at most m times, which gives rise to our tighter analysis of Prim's algorithm, so that the number of calls to decrease key is at most m, which is a better analysis if the number m of edges is subquadratic, if the graph is sparse. That's what's called a sparse graph. Okay, so at this point, we take a small break, and to record attendance. So no, this time we don't have a quiz, just please post your name. And we are back. So thanks for recording attendance by posting your student ID and name in the chat. And we thus can resume the lecture. We have just finished discussing Prim's algorithm, about the correctness of Prim's algorithm for producing a minimum spanning tree, and analyzing the computational cost incurred by Prim's algorithm. And Now we want to discuss another algorithm also for the minimum spanning tree problem, an algorithm that arises from kind of growing a forest. So that's an interesting alternative perspective on minimum spanning trees. So Prim's algorithm would consider one partial tree that would gradually grow to become a spanning tree, whereas Kruskal algorithm considers a forest of trees, a spanning forest that comprises all vertices of the graph from the very beginning, and then gradually merges individual trees in that forest. So remember that a forest is simply a collection of trees. So we consider here a forest, a collection of trees, and initially we just make trivial trees that consist of one vertex each, and each vertex is a separate tree, a trivial tree, and that's of course a spanning forest because every vertex is covered trivially. And then this is the main loop of Kruskal's algorithm. While we have edges left that are not part of the that are not considered yet, and while the forest is not yet covering the entire graph, we again extract an edge. So this is again an implicit call to a priority queue. We extract, no, that's not true. Let me take that back and say more about it, how to implement the next crucial operation, extracting an edge of least weight, and then see whether this edge connects two different trees of this forest. So F is a forest. If the edge connects two different trees of that forest, then merge the two trees, thus reducing the number of trees in the forest. Merge the two trees by adding the edge to the final output set of edges. So again, let me illustrate that abstract idea with an example run on the graph that we've already seen before. So initially, every single vertex is considered as one trivial one element tree. And now we choose and merge two of these vertices of these trivial trees. And the two trees that we choose and merge here are the ones with that are connected by an edge of least weight. And the edge of least weight here is, of course, the edge here having weight 1. So we connect both of them and thus have created a first non-trivial tree that comprised of these two vertices. Okay, that's our first iteration. Next iteration, again, choose an edge of minimal weight. What is the next edge of minimal weight apart from this one, which we've already dealt with and thus discarded? This is the next heavier weight, edge of heavier weight, this one. So we're going to add that edge and thus merge this tree with this singleton tree, and thus create a larger tree and reduce the number of trees in our forest, right? So whenever we merge two trees, that means that the number of trees decreases. Initially, the number of trees is n, one tree for each vertex. And once the number of trees has decreased down to 1, then the forest has become a single tree. And the loop invariant of Kruskal's algorithm is that at every single stage, the forest is a spanning forest. So that at the end, once the forest has boiled down to be a tree, it is going to be a spanning tree, right? So let me say that again, loop invariant. At each stage, at each round, the forest is a spanning forest. In each round, the number of trees in the forest decreases by 1, so that in the end, when the number of trees has boiled down to 1, when there's only 1 tree left, then that single 1 tree will still be a spanning forest by loop invariant, and therefore a spanning tree because it's the only one. Okay, good. So moving on, we have thus continued our simulation of the algorithm on this example graph. And in the next round, the algorithm is going to pick an edge of least weight that has not yet been dealt with. And this is the edge with weight 4 here, this one. And thus connecting these 2 singleton trees into a non-trivial tree of these 2 vertices. Okay, next round, consider edge of least weight. This is the weight 5. Merge the 2 trees, merge this tree with this trivial tree to form a tree of 3 vertices. Next edge, next larger weight is this one that has weight 6, and merge these 2 vertices. Next larger edge, there are 2 choices now, right? This one has weight 7, and this one also has weight 7. So which one are we going to pick? Let's say we pick this one first, but now comes the important condition here. If the edge we've extracted connects 2 different trees, only then the algorithm will actually perform an operation in this iteration. But this edge does not connect to different trees. It connects within 1 tree, and therefore adding this edge would violate even the tree property. It would create a loop, right? Adding an edge in a tree between 2 vertices in a tree will create a loop in the tree and thus violate the tree property, which is not going to happen here. So because of this condition, so this edge is going to only be touched and then immediately discarded for 1 iteration of the loop. Instead, the next iteration, or the first one, whatever, will look at this edge, and this edge actually does connect 2 different trees in the forest, this tree and this tree. So this is a great way and illustration of this condition here, that the importance of this is if statement. Only if the edge E connects 2 different trees, then it is added. Otherwise, it is immediately discarded to avoid creating a loop and thus violating the tree property of the trees in the forest. So this is what happens next, right? We add this edge. Next edge up is the edge of weight 8. There are 2 ones, this one. But again, this one is within a tree, right? So here we see a tree, and this edge connects 2 vertices within the same tree. So this is going to be discarded. And the other edge of that also has weight 8 is this one. And this one does connect to different trees, namely this one and this one. So next, this edge is being added. And this is the end. Well, we can see that the algorithm cannot see it yet. So the algorithm will now look at the edge of weight 9. But this is again an edge that connects 2 vertices within the same tree. It thus gets discarded. Edge of weight 10 is discarded, edge of weight 11 is discarded, edge of weight 12 is discarded. So the final iterations of this OR loop are basically just discarding edges and never satisfying the condition of the if statement, and therefore never really proceed to the core, to the body of the innermost loop. So yes, that's what happens here. And now I've already argued about the correctness of Kruskal's algorithm, right? Correctness of Kruskal's algorithm is based on and relies on this invariant that at each iteration of the algorithm, what it's maintained is a spanning forest. So what is a spanning forest again? A spanning forest is a forest, so it's a collection of trees that comprise all vertices of the original graph. So either 2 trees are either part of 2 different, 2 vertices are either part of 2 different trees, or part of the same tree within the forest. But any vertex in the original graph must be part of that forest. Okay, and yeah, it's a forest is a collection of trees, so there are no cycles either. That's a loop invariant, and that is maintained through every iteration of this outer loop. As we can see here, the edge that is added is only included in the forest if it connects two different trees, thus avoiding to violate the tree property. And also it never gets discards any vertex, and thus maintains the spanning property of the forest. So at every iteration, this is indeed a spanning forest. And right, and why is it a minimum spanning forest? Yeah, because of this operation, the way the edge is chosen, it's always choosing an edge of least weight. So that this is another instance of a greedy algorithm, namely choosing an edge of least weight in a greedy way to add to the spanning forest to merge two trees into forest. So yeah, that concludes our discussion of the correctness of Kruskal's algorithm, and now we proceed to the cost analysis of Kruskal's algorithm. So here, extracting the edge of least weight, I have to correct my initial statement. This is not, we do not use maintain a priority queue for this purpose. But indeed, as you may have noticed from the example execution, the algorithm just processes the edges in increasing order. There's no decrease key operation, no call to a decrease key operation. So we don't really need a priority queue here. From this perspective, Kruskal's algorithm is in a sense conceptually more simple than Prim's algorithm. So the only thing we really need here is to have the edges originally stored in increasing or non-decreasing order of weight, and we can use a simple array, an array of m elements to store the m edges in non-decreasing order of weight. And let us, we can achieve that by simply sorting the edges in increasing order of weight, using, for example, merge sort or quick sort with our linear time median pivot search. So let's simply suppose that the edges are already provided in an array of non-decreasing weight. Then extracting this edge actually has constant cost, right? And we just need to pick the next edge in the array. No need to remove an edge from the array, just maintain a pointer, which edge in the array we're currently considering. So that's constant cost. And how often is that constant operation executed? Once for each edge, right? So in each iteration of this loop, one edge is considered and either added to the forest or discarded, so that this operation, this outermost loop, is executed m times, right? Once for each edge. And this operation has the constant cost as part of the loop body. How about this operation? This is the crucial part. If the edge connects two different trees, how can we implement a data structure that allows to check whether a given edge, a data structure that maintains a forest, it allows to test whether an edge connects two different trees in that forest, or whether the edge is within one tree in that forest. That's the first question. The second question of the data structures, how can we merge two trees in that data structure? So let me say that again, because that's really crucial, and that what's deeply differs Kruskal's algorithm from Prim's algorithm. We need here for Kruskal's algorithm a data structure that maintains a tree, a forest. Data structure that maintains a forest on a fixed number of vertices, and the data structure is supposed to support two operations: test whether a given edge connects two different trees, or the opposite would be with that the edge actually is part of a tree already. So whether the edge is between two different trees or within connects two vertices in the same tree. So that's kind of a first property. And the second property is adding an edge, or put differently, merging two trees in that forest. So these are the two operations: test and combine. We need a data structure for that. And the extracting operation is not the crucial one. They can simply use an array for that purpose. And that array doesn't even change. So it's just the initial sorting and then constant operation for that. So the data structure for maintaining such a forest is called union find data structure. It's a very interesting data structure with various implementation, and the most efficient implementation has an overall cost for m, right? M iterations, m calls to this operation and to this operation, has a cost of m times alpha m, where alpha is the inverse Ackermann function. Now you may or may not have heard about the Ackermann function and its inverse in discrete mathematics, course CS204. But in either case, so the union find implementation of a forest data structure is an advanced topic in algorithm design, and even more so in algorithm analysis, and is not covered by CS300. Instead, it's covered by CS500. So let me do some cross promotion to CS500 here. About the design and analysis of the union find data structure. But now we just stop the more detailed analysis of Kruskal's algorithm here, and summarize the algorithms that we've seen so far for the minimum spanning tree problem. So the first was Prim's algorithm that would start with a singleton as a partial spanning tree, and repeatedly, iteratively grow that partial spanning tree to become an actual spanning tree. Whereas Kruskal's algorithm will start initially with a spanning forest of singletons, and would gradually grow that spanning forest to gradually merging two carefully chosen trees in that forest, so that in the end the spanning forest decays into a spanning tree. And that spanning tree is going to be a minimum spanning tree. And both Prim's algorithm and Kruskal's algorithm has this interesting property of being examples of greedy algorithms because of the way they pick the edges. So Prim's algorithm picks an edge of least weight, picks a vertex of least distance to the partial spanning tree, and Kruskal's algorithm picks an edge of least weight to be either added or discarded into the forest. So that's our summary of the two important algorithms for minimal spanning tree problem. Let's now move on to consider another graph problem, namely a flow problem. So what's the purpose of a flow problem? Let me illustrate that again with a graph. And this time we're talking about directed graphs. So what you see here is a graph on 6 vertices labeled with letters. And also you see directed edges between these vertices. And these edges are labeled here with 2 numbers. So let me explain the 2 numbers. And most important, let's focus on the second number first. The second number here is, for example, 3, 3, 2, 3, 4. This is to indicate the so-called capacity of the edges. So what I'd like you to imagine here, that these edges kind of correspond to pipes. Okay, so the pipe that maybe can bear a certain amount of water or sewage or whatever, draining pipe. So that means this pipe, let's just say it has diameter 3, or can, no, diameter is not a good measure, it's quadratic, but anyway, so it can bear 3 liters per second, let's say, also 3. This can only carry 2 liters per second, 2 liters. This can even carry 4 liters per second, and so on. So this is why it's called a flow problem, because edges correspond to pipes that can bear a certain flow of some commodity, a liquid commodity. And so that's the second number, how much the pipe can bear without bursting. The second number is how much the pipe currently actually is bearing. So for example, this pipe can bear 3 liters per second, but in the current configuration, the current demand and of how much people flush down the toilet, currently they flush only 2 liters per second are being flushed through this pipe. So this is the interpretation of the first number. This pipe is currently, for example, is unused, right? So it can bear up to 2 liters, but here the first number is 0, which means that currently the pipe is not used. There's nothing running through the pipe. It's kind of, we could actually remove the pipe, this pipe, without changing anything in the flow. So to summarize, this picture, this describes two things actually. First, how much the pipes could bear, each pipe individually. And secondly, the picture indicates a current flow, that current state of the sewage system, how much is being run through the pipes. And that's indicated by the first number. And the important property is, of course, that the first number must always be less or equal to the second number. If the first number exceeds the second number, that means the pipe is bearing more than it can and will burst, and disaster will strike when the sewage hits the fan, literally speaking. All right, so here we have already arrived at the condition of a flow, namely that the actual flow must always be less or equal to the value of the what is feasible for each pipe locally and individually. So also being directed edges, yeah, we'll talk about the direction of the edges in a minute. So for now, let's only consider the second numbers that are non-negative numbers. So that every edge actually is able to bear a certain amount of fluid per minute or second, like here. There's no edge from here to here, so that means there's no direct way of connecting, of from proceeding flow from here to here. But of course, we can make a detour here. But this detour has to be added, or we can take this detour, right? So that means anything we want to send from here to here could be split actually, right? So we could split it like a half part going this way and half part going this way. This is perfectly fine. And that will, however, add to what is already going through these pipes from the source. So this here is called the source. This is where all the water comes from, because there's nothing entering, no edge entering the source. This is the target. This is where the drain. This is where all the fluid in the end ends in, because there's no outgoing edge. And in other or any other vertex must there's nothing, no water miraculously appearing nor miraculously disappearing in all the internal nodes. So, for example, anything that comes into this node must also leave the node through either of the two outgoing edges or split between the two outgoing edges. Anything that enters this node must also leave the node. So that's the point about internal nodes. Internal nodes have this important property that everything that enters the node must also leave the node, except for the source in target. The source node is a node where nothing enters and only something leaves, something that miraculously enters. Maybe there's a toilet on top of the source node, and this is the target node, the drain. This is where everything ends up in and is miraculously disposed of from here. So these are the three types of nodes: one source node, one target node, and internal nodes that where no flow appears or disappears. So that's the picture here. And now let's generalize and formalize this interesting graph problem. But first, let me emphasize what is our algorithmic problem here in the end. So the algorithmic problem is the following: given such a directed graph, that's an input, as you see here, specification, right? Given as input a directed graph, not necessarily acyclic actually, but we'll discuss that in a minute. The benefit and disadvantage of having a cycle in the flow problem. So the input is the graph, and the graph is weighted. Namely, the second numbers are actually the edge weights, non-negative integer edge weights. The first numbers are not part of the input. Let me emphasize that, it's important. The second numbers are part of the input. And the goal is to devise a flow that is to find first numbers that satisfy all the constraints, so that the first numbers are never exceed the second numbers, never make the pipes burst, and such that there's the largest possible amount of commodity can flow through that path from the first to the source to the target vertex. So in this example, the flow, the first numbers, the collection of first numbers amount to 5 liters per minute being drained from the source here, right? 3 through that edge and 2 through this edge. So a total number of 5 liters per let's say per minute is leaving the source. And you notice that also a total number of 5 liters per minute is entering the target vertex, right? Is that coincidence? Well, it's not, right? Since we have the conditions that at every internal vertex, whatever enters an internal vertex must also leave an internal vertex. There's no commodity miraculously appearing at internal vertices, nor disappearing at internal vertices. Therefore, the only anything that enters the whole network through the source must also leave the network through the target, and therefore the total commodity flow here is indeed a 5 here, measured here of here. And the algorithmic problem that we're considering is find a maximum flow, find assignments of flows to the first numbers that are less or equal to the second numbers, the constraints, how much the pipes can bear, and that maximize the total flow. So we want to push as much as possible through the pipe network without making it burst. That's basically the idea of the algorithmic problem we're considering. Okay, so after this having provided the intuition, let's now proceed to formalize this problem by defining what is the flow in a directed graph with non-negative edge weights. So we have this graph, directed graph with non-negative edge weights, and the definition says a flow from source vertex to target vertex in that network with weights, right? So this is the weights of the flow as opposed to the weights of the edges. Is a mapping that maps to each edge the amount of commodity that goes through that edge and that maintains, that satisfy this transition property that for all vertices that are internal vertex, for all vertices that are neither source nor target vertex, the total flow entering the vertex, that's what you see here, right? So everything that no, that's yeah, everything that enters vertex V through some vertex U that is connected to V in the direction. Remember, this is our terminology for directed edges, right? From U to V. Anything that enters in that way must also leave from V through some neighbor vertex W and directed edge from V to W. So that's a condition. Yeah, it's a kind of transition condition, continuity condition. No commodity can enter or leave except through neighbors for internal vertices. Exception is always the source vertex and the target vertex. And the flow is admissible if it satisfies the constraints of the pipes. So the amount that actually flows from vertex U to vertex V in this assignment, right? So must always be less or equal than the flow that the pipe can actually bear, which is part of the input. So the input is the matrix A of the graph with its weights, and the algorithm is supposed to find a flow that is admissible. Two conditions: must be a flow, nothing graded nor lost internally in the network, right? So when there's something lost in the network, that means there's a broken pipe. We don't want that. And secondly, it must be admissible. Any edge must bear only as much flow as it can bear without bursting. That's the two conditions. And subject to these conditions, these are called constraints. The graph problem is to find a maximum admissible flow. We say that again. The max flow problem is the problem given a directed graph with this weight matrix, find a flow which is admissible and maximal among all admissible flows. It's our definition of the maximal flow problem. And now we proceed to discuss algorithms for the maximum flow problem. So the goal is to maximize the flow, and we can measure the flow in various ways. So for example, we can measure the amount of flow that leaves the source vertex, right? So S here is our source vertex. V is all neighbors, all outgoing edges, and sum over all the flow that leaves the source vertex. Equivalently, we can also say maximize the flow that enters the target vertex, because as we mentioned, continuity conditions at each internal vertex mean that both are the same. So maximize that for a flow F from source to target vertex that is admissible. and that is to be output a maximum flow as usual. So to be perfectly formal, we're asking for the value of a maximum flow, because the maximum flow itself need not be unique. Sometimes we can kind of shift part of the flow internally from one pipe to another when these internal pipes are not the crucial constraints. But what is unique is how much is leaving the source node, which is the same as how much is entering the target node, whereas the details of the flow on internal nodes need not be unique. So we're only interested in a maximum flow and don't really care about which ones, how we don't have a preference about non-uniqueness for internal pipe capacity usage. So, right, so time is already up. We have not, we will proceed to discuss algorithm for the flow problem in the next session. Let me conclude by emphasizing we're only focusing here on integer, non-negative integer weights. There's a reason we can also consider positive real weights, but for now, let's restrict to integer weights. Dealing with real numbers, again, is an entirely different problem. And we'll discuss algorithms in the next session. Right, so inflow and outflow are the same. And an important purely mathematical statement says, which is not at all obvious, that if we have constraints on the internal edges, on the internal pipes that are only integers, as we suppose here, then there always exists also an integral maximal flow. We say that again, this is a take-home message, the cliffhanger, right? That keeps you curious about how we continue. So in general, even although the weights of the internal edges may or may not be integral, even if the weights are integral, then there's still possible that the maximal flow is not integral, that uses fractions, non-integer real numbers. But if so, then the lemma says that there exists also a maximal flow which is integral. So this is an important illustration of the non-uniqueness of maximal flow. But time is up for now. I understand that this is a subtle point, so I promise to explain it again and in more detail at the beginning of next lecture. For now, thank you very much for your attention. Have a great day and see you next time.